All right, guys, if y'all look at your test objectives, this is probably the most important thing because I went back through the test yesterday and I made an emphatic point in my brain of, wow, these things are super important because I'm not kidding you. Everything that's on the test is listed in these test objectives. So what I'm going to do is I'm going to try my best and most possible to try to get through this as much as possible. One more time to reiterate, tomorrow afternoon starting at 3:30 I will do a review session, and if I don't get to it I will cover it in the review session, and I'll cover whatever you want me to cover. But I want to hit these things because everyone can be here because I feel like they're the most important because it is the things you're going to be seeing. Alright, number one, be able to calculate certain variables of a gas using Pivner, which is the ideal gas law. So let's just talk about this real quick. So PV equals nRT. This is called the ideal gas law, but we need to talk about these things. What does P stand for? It is your pressure. Okay? What is the most common unit of pressure? Alright, so this is where we're going to start. So we're going to start with pressure. Okay? The most common unit is ATMs, right? Which stands for what? Atmospheres. I'm just going to jot this down. Atmospheres. Okay, so this is what is most commonly used. However, there are other units. What is another pressure unit you may run into? Okay, millimeters of mercury. Okay, does anybody remember how that unit came about? Remember? Torricelli, right? The barometer. How much atmospheric pressure was pushing down did what to mercury? Pushed it up that tube, right? And the 760 was how far that mercury moved. So it was 760 millimeters of mercury in how many torr? Excuse me, in atmospheres. 1 atmosphere. So if I have 1 atmosphere, I have 760 millimeters of mercury. Do you guys agree that this is a ratio or a relationship? Same concept. If I have why is this thing so slow? If I have 1 foot, what do I have? I have 12 inches. Is that pretty much the exact same concept? Why is the top one harder than the bottom one? You're not used to it. You've never heard it. You've never experienced it. Is it the exact same thing? Go ahead, Nick. Okay. This, I do not think so. No. If you want, it's not going to show up on test day, so I wouldn't do that. That's just something you need to commit to memory. Okay? Now, just throwing this out there, there's also another one you may see. This right here is equal to the guy who did it. Who was the guy? No, is that his name? Something like that. Tortellini, yeah. Torricelli. So 1 atmosphere is equal to 700 millimeters of mercury or 760 torr. So Torricelli did the millimeters of mercury. So are they the same? Yes, okay, and it's 760 for each. Just regular mercury, just old pure elemental mercury. So this is something that's important. So what I want you, don't highlight this, but remember this in a minute because we're going to have to come back to it. Okay? Number 2, what is V? Volume, all right? So we know that V stands for volume. Is there anything hard or difficult about that? What is the unit that we're probably going to most likely be needing to use? What? Liters. Okay? Make sure you comprehend that. Liters is very important. All right, N. This is the weird one. This is the number of moles. What do you think those AP people are going to do to you? Bingo. Be careful with this. Most of the time, they're going to give it to you in grams, okay? So be very careful about this. So when you're doing this one, look for grams. How do you get it to moles? Divide by mm. And what is mm? Molar mass. Okay, how do you get molar mass? Off that thing hanging on the wall. All right, let's skip one. What is T? Temp. There are only a few cases where we ever use 1 unit. What's the one we must always use? Kelvin. Very good. This one must be in Kelvin. All right, so let me go back over here. Let me add another page right here. So let's talk about temp for a second. If I want Kelvin, how do I get it? It's Celsius degree plus what, Nick? 273. If you do not have that memorized, you need to very, very, very quickly. Okay? Just some common ones. What is 0 degrees Celsius? 273. Duh. All right, what is 25 degrees Celsius? 98. Those are the two that you will run into most often. Those are the two you need to commit to memory. The top one's the easy one. That's simple. The bottom one, most things are ran at 25 degrees Celsius. So if you've written this part down, there's another little note that you can make for this. This is what is called standard conditions. It's between 74 and 77 degrees Fahrenheit. I can't remember the exact value. But in this room right now, or outside, if it were 74 to 77 degrees, would you be okay with that? Absolutely. In here, it's a little warm-ish, but outside, that's a beautiful day, right? That is a nice fall, crisp day. So, what? If it were 77 in here, in room temperature, 77 is a little warmish because we're used to 73 to 75. 77 is a little warm in a house. Some of you sleep on, 62? Some people, it's absurd. So, here's how I want you to think about it. This is kind of like weather conditions. Okay? If it were 77 degrees outside, it'd be the best day ever. I'm sorry, I'm a fall person. I don't like the hot heat. It's not summer. It's not winter. Love it. Now, here's the deal. I need to point something out. Again, I'm just adding this bonus information. Standard conditions. And again, I don't want to waste a whole lot of time on this, but it is something important. You probably don't have to write this down, but same or different? Different. One key indicator. This is at 25 degrees Celsius. This is at 0 degrees Celsius. That's the biggest difference. So when you hear someone say standard conditions, they're talking about weather conditions. If you're in a lab, would it be 0 degrees Celsius? I hope not. Why? That's really freaking cold. But if it's 25 degrees Celsius, could you tolerate it? Yeah, that's a regular room condition. So this is standard conditions versus STP. This right here is the most misconfused thing about any type of calculation and when to put numbers in, is students get these confused all the time. We're just going to have to do our best to try to remember which one is which. There's no other way to do it, but just remember and memorize it, okay? All right, so going back to this. So we know that we have liters, we have Kelvin, and so finally the all-important R value. Now, we've talked about pressure, we've talked about volume. What things have pressures and volumes? Gases. These two things make us have gases. So which R would we be using, the gas or energy R? The gas R. So this really is our gas R. Does anyone remember the numerical part of this? Okay, 0.0821. Now, I'm going to write it beneath it, but obviously the unit will go right here. I'm just not going to cram it into that space. So, we know that, watch this real quick. If I take, and I love doing this, so PV equals nRT. Rearrange that for R. For R, PV over NT. If we take this and we do this at STP, what is your pressure at STP? 1 atm. Here's the tricky one. What's your volume at STP? 22.4 liters. How many moles? 1 mole. Remember, and I told you, at STP, it's what? Not 0, 273. And you know what? I'm so glad you said that. So let me go back to this real quick. This is, and if you've made this little note, this is 298 Kelvin. I should have written this down, and I'm sorry I didn't. So if you wrote that, just add those two numbers. 25 is 298, and STP is 273 Kelvin. So, my first question to you is, if you plug these numbers into your calculator, what do you think your answer is going to be? This is where the R value comes from. Number two, do any of those units cancel? So what is your unit? Alright, so this is the way I say it. Let me come back to this. I say it as latum over mole. It's just an easy, quick way to remember it. So latum, liters times atmospheres, over mole times Kelvin. Everybody okay with that? All right, so my question is, if I give you 3 of the 4, now why am I saying 3 of the 4? Because isn't there a fifth variable? It's constant, very good. Which one of these do you never have to have given? R. R is always 1. So if I give you 3 of the 4, could you solve for it? Yes. One little quick quiz. Solve for n. Just want to see if you can do it. No. Algebraically. P V over R T. Let me think for just a second. No, I'm just talking about in general. See, that just won't work, will it? If I need P. I'm just seeing if it would work. All right, so you should be able to know how to do that. Number 2 in the test objectives. So again, that was a whole little lecture on PivNerd if you've never seen it before. Number 2, be able to write reactions, including synthesis, decomposition, and acid-base. Pay special attention to specific types of decomp, such as metal carbonates. Okay, so here's what I want to do. I'm going to pop this up here, and just because it says this specific one, metal carbonates decompose into what 2 things? A metal oxide and CO2. A metal oxide and CO2. So let me just give you a basic example. So if I gave you, come on, PbCO3, lead carbonate. Now, here's the tricky part. Which lead? Why 2? Because carbonates are 2 negative, so what happened to the charges? They cancel. So what would this turn into? Lead oxide. Which lead? Lead 2. So it's 2 plus and 2 minus. So what happens? PbO plus CO2. Everybody with me on that? Devin? You good? This is just something you have to memorize. Is this a metal? Is this a carbonate? So is this a metal carbonate? Is this a metal? Is this an oxide? So is that a metal oxide? And this is obviously what? Carbon dioxide. So metal carbonates decompose into metal oxides plus carbon dioxide. Do you want to see another one? Okay. What carbonate is that? Silver carbonate. What is it going to decompose into? Silver oxide. Now be very careful. What is silver's charge always? 1 plus, oxygen is 2 negative. So what's your formula? Ag2O plus CO2. Basically, if I gave you a compound and said, write the decomposition reaction, this is what it would be. Yes, sir. That's what I'm fixing to get to. Now, let me ask you this, because this is also an important topic. If I asked you what type of reaction this was, how would you label it? Decomposition. What if I asked you what is the reverse reaction called? Synthesis. So how could you state this reaction in reverse synthesis form using words? No, not compounds, in words. What is that thing and that thing plus this thing makes that thing? A metal oxide mixing with carbon dioxide create a what? Metal carbonate. So our decomposition and synthesis reactions the complete and total opposite. So if something decomposes one way, if you reverse it, can you create it? Yes. So you don't have to memorize them as individual things. They are actually complete total reactions. Now, are some very hard to do in real life? Yes. Remember when we talked about this, and some of you have seen this and some of you have not. It's not sine and cosine. Is that total? Yeah, those are different. What are the difference in these reactions? My students better know this. Okay? What are these two graphs representing? Energy. What is delta H? Enthalpy. What is enthalpy? Energy. All right. So what we're talking about here is the amount of energy required to make a reaction start. So do you agree we have reactants here and products here? Reactants here and products here. If I gave you a soccer ball, Nick, and asked you to make it to get to the products, which side would be a lot easier to do? The right side. Okay? The right side, do you agree that it would be spontaneous or non-spontaneous? It would happen in nature more efficiently. Okay, so do you agree that this would be what we call a spontaneous reaction? Okay, does anybody remember in thermodynamic terms which one was spontaneous? Very good. It is exothermic. Have you ever seen this? Who has never seen this? Good, you've at least all seen it. So what is the opposite? Endothermic, right? Okay, endo, and this is non-spontaneous. Now, in honors chemistry, I use the word spontaneous and non-spontaneous because you've heard those terms, right? Well, in AP, we have a new term because they want you to sound a lot smarter, and it's this word. I'll come back to that. Give me a second. So spontaneous is now thermodynamically favorable. Or never, ever write this on a test. Please. Instead of saying thermodynamically favorable, it takes 8 seconds. I say TF and I move on. Okay? All right, you would. So the whole purpose of this is that I want you to understand that it's all based on energy and how we take synthesis and how we take decomposition reactions. One of them nature is going to prefer. Nature likes it because it's the easiest to do. Nick, I asked you the question. You said that if I gave you a soccer ball, this one would be a lot easier to do, right? So do you agree that if it's easier to do, you could give energy off to that kid? Yes, which means you have energy to give out to the system. But what would you have to do to make this one happen, Nick? In terms of this, I would have to apply more energy. So if I go back to this reaction, do you agree that nature can take some energy, supply it to this, and break it apart and be done with it? But what would it require to make this happen in reverse? a lot more energy. Is nature willing to spend as much energy to put something together as it is to take it apart? No. This just happens to be for this reaction. Are there others where it's easier to put it together than break it? Yes. And that's where you have to look at bond energies and bond types. So we can get into that. So Colby, you asked a specific question. Let's look at another example. How would you name that compound? It's potassium something, but general name. It's a metal chlorate. So this is a metal chlorate. True or false? True. A fact is, metal chlorates decompose into something. All right, so let's pause right there. So we have a metal chloride. Okay? Ide, because it's going to be just O. Excuse me, no, it's going to be Cl. What am I talking about? So, metal chloride. This is chlorate. Why is it 8? ClO3 is 8. You with me? Okay. So, what would our example formula be? What is a metal chloride in this example? KCl. Why is it just KCl? Where are your charges? 1 and 1, right? 1 positive, 1 negative. Now, metal chloride and what? Very good. Oxygen gas. So, if you take this and plop this in, you're finished, right? No. Why not? Why is it O2? It's a diatomic. Now, obviously, this is still incomplete. Why? It's not balanced. Some of you have heard this. Some of you have never heard this. This is what I call the 2-3-6 rule. Anytime you see a 3 on one side and a 2 on the other, what is the least common multiple? 6. So if I give the 3 a 2, how much did I create? A 6. If I give the 2 a 3, I create another 6. Well, what is the only thing I have to do now? Put a 2 in front of KCl and you're done. Okay, balancing is always a part of this. So when you see this on the test on Monday or Thursday, when it says write a chemical reaction, what must you also do? Balancing. What? Okay? All right, everybody good on that? All right, well done. Number 3, be able to compute the empirical formula if given percent composition, lab data, or combustion. All right, say it again. Yes, for right now. We're going to get into other ones later. Just those 2. Just make sure you know those 2. Yep, but there's hundreds of them. We'll talk about a lot of them later. All right, so what I want to do is I want to get into the packet. So this was actually in your packet of notes that you guys did over the summer. And some of you probably breezed through this and didn't pay any attention to it. What? All right, so making sure you know empirical formula. What is empirical formula? Simplest small whole number ratio, period, bottom line. There are 3 ways to be able to solve for it. I don't know that. 3 ways. Number 1, percent composition. If they give you percent, what must you do? Drop it and change it in grams. That's super easy. Don't ever mess that. Number 2, lab data. This is where it gets a little funny. Basically, it says we have a compound of 2 elements. The entire mass of the compound is 12 grams. One of the elements weighs 4 grams. What's the empirical formula? Well, obviously, they did not give you data about one of them. What must you do? Just solve for the missing one. By what method? Subtraction. Okay, does that make sense? Super easy. The last one is the hardest one. And guess what you probably potentially might see Thursday? The hardest one. Determining the empirical formula through combustion. All right? So here's the way you're going to get it. So if you want to go back and watch this part of the video, I would highly recommend it because I'm not going to spend time going over the problem because you have that at your disposal. Determining the mass of carbon, hydrogen, and oxygen. Now, whenever we do a hydrocarbon, most hydrocarbons have to have what elements? Carbon and a hydrogen. Are those the only 2 things present? No, AP Bio students, whenever you saw large organic molecules, there was two other elements that you saw all the time. What were the other two? Oxygen, most definitely. And what was the other one? So who said it? Nitrogen. That was the other one. So, here's the deal. You've got to be able to decipher which element is present in the compound. The easy ones are carbons and hydrogens. You can fly through those. But as soon as they kick this oxygen in, you've got a problem. And if they ever throw in the nitrogen, it makes it more complicated. But the base steps are still the same. The whole entire key is determining, if you have all four, the original amount. Now, in something in chemistry that makes our lives a whole lot easier is that we have something called the law of conservation of mass. True or false? What is the law of conservation of mass? Okay, that's essentially what it is. Matter cannot be created or destroyed. What you start with, you must end with. So if you start with a certain amount of grams of carbon, hydrogen, nitrogen, and oxygen, shouldn't you also end with that amount? Yes. So if you can determine the original amounts of all of these values, then the process to find the empirical formula stays the same no matter which three ways we're solving. And we're going to get into how you solve the empirical, but I want to focus on this part because this is the most challenging. Okay? So if you do have a hydrocarbon, and let's actually talk about this for just a second. So if you have a hydrocarbon, if you've got a carbon, let's see, C, what's the last? RSTV. What's the next letter? W, X, well, I started wrong. Y, thank you. I should have said W. So basically, what are V, W, X, and Y? Any subscript, right? If this is a combustion reaction, what do you always have to have present in combustion? Oxygen. That's what makes it combustion. And the products will normally be what two things? CO2 plus water. Well, here's the deal. What throws a kink into that hypothesis? Nitrogen. Because what do we know about conservation of mass? What you start with, you must also end with. So there is, depending upon which organic molecule you have, there's two possible choices. You can have nitrogen monoxide or nitrogen dioxide. It just depends upon which chemical formula you're coming up with. But do you agree that no matter what, N is still present on the opposite side? Yes, and so you'll have to worry about that in just a minute. So here's the deal. So if I want to know how much each original amount is working with, there's really only one way to do it. And I've listed the steps here. Number one, determine the mass of carbon in CO2. Why can I do that? Can I get carbon from CO2? Carbon is one place on the left and one place on the right. So if I have a certain amount of carbon here, is the exact same amount over here? Yes. So if you know how much carbon dioxide you have, could you find out how much carbon is present? Yes. My second question, how can I find how much hydrogen I have in my original amount? Water. So if I know how much hydrogen I have in my water, can I find out how much I have of hydrogen? Yes. Why is this difficult for oxygen? It's in multiple places, right? Over here, it's in carbon dioxide, and it's also in water. So let's take this simple step first. So let's look at, let me just kind of roll through this, because if it's already listed in there. So determine the mass of carbon and CO2, determine the mass of hydrogen and water, and get the mass of oxygen through subtraction. Yes, ma'am. You got a question? You got a question? Okay. All right. Only difference in one step is the first step. So we'll talk about this. We'll get back to that in just a second. All right, so let's just look at this example. Do y'all have this? All right, so combustion of 5.23 grams of phenol. Now, you guys don't know this, but phenol is CXHYOZ. Because phenol contains only carbon, hydrogen, and oxygen. What's the empirical formula? So if we've already worked this, that's fine. If you want to go back and see it again. But the first trick is I need to know how much carbon is in this thing. True? So what do you have to do? Of that 14.67 grams, I want to know how much of it is what exactly? Carbon. All right, so I've got 14.67 grams of carbon. True or false? True. Yeah, thank you. Carbon dioxide. I'm going to make life really easy for you guys. Do you agree that gram of CO2 would go on bottom? I'm going to make this very easy, and this is totally against stoichiometry rules, but I'm going to go ahead and do it. I'm going to jump right into grams of carbon. Why is that possible? It's a 1-to-1 ratio. So, what's the mass of carbon dioxide? Does anybody know that? Very good, 44.01. Of that 44.01, how much of it is carbon? 12.01. So do you now agree that does anybody have the number written down by chance? What is it? 4.0, just 4 even? Oh wow, okay, well that's worked out real nice. Do you agree I now have my amount of carbon? Why is this true for the original? Because what you start with, you must also end with. So I had to start with exactly how much carbon? 4 grams. Okay? Now, this is the tricky part that always throws students off. I've got 3.01 grams of water. So, does grams of water have to go on bottom? Yep. Now, is this atom to molecule ratio 1-to-1? No. But if I did it very simply, could I still go to grams of H? Yes. But if my mass of water is 18.02, of that 18.02, how much of it was exactly hydrogen? 2.02. This right here is where students mess up the exact most, because what do you want to put right there? Ooh, that's not the right button. You want to put 1.01 because that's what you're used to putting. But of the 18.02, 2.02 of it is exactly hydrogen. So, you'll have that answer too, correct? What is it? Okay, 0.337 grams of what? Hydrogen. Now, do you agree we know the original starting amount of this entire compound? What was it? I know 2 of the 3 parts that made it, correct? What are the 2 parts that I know? I know carbon and I know hydrogen. Well, how do you find the missing link? Just subtract. Yes, sir. So the formula is going to be CXHYOZ, and you're trying to figure out the X, Y, and Z. You're trying to figure out the subscripts. Yeah, that's the product, the amount of product that was produced. Yep. So you started with 5.23 grams of phenol. I said, here you go. Now go and light it on fire. And in the end, you were able to deduce that 14.67 grams of product of carbon dioxide got produced, and 3.01 grams of water also got produced from the original 5.23 grams of phenol that I gave you. You with me? That makes sense? So now, obviously, how would we find the amount of oxygen? Subtract 5.23 minus 4.00 minus 0.337. 0.337, and y'all have that written down. What is it? 0.893 grams of oxygen. So, the whole purpose of this part was to find the original amount of each element. True or false? True. From this point on, is it just like the basic, easiest, simplest empirical formula problems? Yes. And so that's what I want to go back and show you now, is that from this point, now that you have all the masses, It should be super, super simple. If you have the mass, what's the next step? Convert the grams to moles divided by the molar mass. Once you have your number of moles, what do? Divide by the smallest moles, and that's when it's got to be within how much of a whole number? 1/10 of a whole number. And if it's not, then what do? Multiply everything by 2. Everything. And what if they're still not within a tenth? What's value by 3? The original. All of them by 3 until you get all of them within 1/10. Okay? Does that make sense? So, has this helped seeing this again? Okay? Now, I'm going to throw this in there at you. What is that? Percent. What does percent mean? Is this also a formula? Does it work the exact same way? So if you know 2 of the 3, can you solve for the missing link? Yes. So let's say that I gave you something and I need to know a part of a whole. And I give you the percentage and the entire value. Can you still determine the part? Huh? How many students are in here? There are 23 students. Let's say that 73% of the students in here are male. How many people are in here? Or how many males are in here? How do you do that? Can you do 73 times 23? No. This is where students also messed up. Percentages are not real numbers. Why? If we're having a 0.25 sale today, is that a good thing to go in and get? Exactly. That's 25%. Or if we're having a 0.75 sale off all clothing today, do people like decimal numbers? No, they like big, whole, huge numbers. So if you see 75% versus 0.75, in your mind, which value is larger? 75. But what do we know about them numerically? They're the exact same. But people like big, whole numbers, which is why percentages were created. Okay? We don't like decimals. We think them as small, tiny, insignificant numbers, even though they're the same. So just be careful and understand that percentages are also formulas. You can work them backwards. You don't have to work them forwards. Okay? Keep that in mind. All right? Number 4, be able to determine the molar mass of a gas. We've already went over the molar mass kitty cat, right? All good cats put what? Dirt over their pee. The problem is MM equals DRT over P. What is D? It is density. It is density. Now, let's talk about that. What is density? Mass over volume, which should have what units? Can it have anything other than grams per liter? It can. It can. Let's just talk about this. I like doing this. We just said that density is what? Gram per liter. Gas R or energy R here? Why gas and how do you know? It's got a pressure. What's your unit for R, the gas R? Note the unit. Latum over molk. All right, what temperature unit should you use here? Kelvin. Pressure unit. Atmospheres. Units. What cancels? Do liters cancel? Do grams cancel? Do atmospheres cancel? Do Kelvin cancel? What 2 units are left? Grams over mole. What were we solving for? What is molar mass unit? Grams over mole. Do units have to work for your math to work? If your units don't work, you've done something wrong. You see how important it is to throw units on it? Got to make sure you put units on everything. All right, the next one. Know how to compute the molecular formula after finding the empirical. Does everybody know how to do that? All right, let's look at it just to make sure we're all good. Again, I think this is in your notes. It's the mass of the MF over the mass of the EF, and we've already looked at those problems, right? If the molar mass of the molecular is given, is that a good thing? Yes. But what if they give you the density? What are you going to have to do? You've got to use the molar mass kitty cat formula to dirt over their P. And the empirical, should you have already found the empirical formula, then you just find the mass of the formula you've already found. And then once you divide them, you should get a whole number, right? What do you do with this whole number? Multiply it times the subscripts, and that will give you your new molecular formula. All right, the next one, calculate the mass in moles of water and the compound from a gravimetric hydrate lab. All right, here's what I want you to do. Do you remember when we talked about the copper and the iodine and how it mixed and the water dripped off and you had to add and subtract and all that stuff? I would go back and look at that. Okay, I would go back and look at that question. Remember, it had like a table, and it had the compound, the copper strip and the mass, the copper strip plus the compound and the mass, the copper strip plus the washed strip and the mass. Go back and look at that question. It's called a gravimetric. No, it's not in the packet. We did it in class. That may have been the day you thought I wasn't doing anything and didn't decide to show up. Okay. Explain how the following could affect a hydrate formula. Too much heating, not enough heating, splattering of the compound. Now, what is a hydrate? A what? It's got water with it. We also call these things dot water, right? So let's just take an example of copper 2 sulfate. Dihydrate. This is a hydrate. Again, how do I know? Okay? We call this thing a dot water because there's a dot and a water. How do I know it's called dihydrate? There are two waters. So let's pretend that we take this thing and we put it in a crucible, and then all of a sudden we take some flame and we heat this thing. What is the purpose of heating a compound that has water in it? To get rid of the water. Let me ask you something. Copper 2 sulfate, ionic or covalent? Ionic. Higher boiling point or lower boiling point than water? Higher. So the hotter it gets, will the copper sulfate stay the same? What's going to happen to the water? It's going to boil off. So think about that. If I boiled it too long or too short, or if it splattered or anything like that, keep that in mind. Like something like got out of the container. That's not good for you.